Welcome to Applied Animal Feeding. In this video, we're going to learn how we can use mathematical equations to predict animal nutrient requirements. It is something that as a scientist or a professional in animal science, we need to be comfortable with being able to understand what an equation is, how they function, and how we can use them in our workplace. So to do that, we've got to have a good understanding of equations, where they come from, and what they can potentially do to help us. So from an objective standpoint, what I hope you apprehend from this video, is to first define what an equation is. Second is to describe how maintenance energy equations are generated, very briefly, and give you an understanding about why we would use some of these. We're also finally going to determine and apply appropriate equations to calculate a specific animal's energy needs. And this is one of those things that a lot of times we know what equations are. We do them in math throughout high school, college, but understanding where they could fit in the workplace and why we need to understand how they work mathematically, because we've got to be able to know if we're getting a correct answer or not. And if you don't know the base math behind something, then it's going to be a little hard for you to determine if you're using a computer system or something that's going to give you a correct answer or not. So when we talk about an equation, according to Wikipedia, that's a mathematical statement asserting two expressions are equal, always containing an equal sign. We really solve for unknown variables all the time. For an example, if you're out to a restaurant and you have a $100 restaurant bill and you need to calculate a 20% tip, sure, most restaurants now put that number on there for you, but is it correct? Is it what you want to do? And so in this case, we'd be solving for X is the amount of the tip. That's the unknown variable. And it's simply 100 times the decimal form of the percentage, or in this case, 0.2. That answer would be $20. So on a $100 bill, if you wanted to leave a 20% tip, that would be $20. But that's just an example of how you use an equation, essentially, in your everyday life. So when we talk about animal nutrition specifically, equations are used a lot to predict nutrient requirements. The National Academy of Sciences subcommittees on nutrient requirements, what we call the NRC, National Research Council, has done lots of species: beef cattle, dairy cattle, horses, and small ruminants and camelids, swine, a tremendous variety of species, including the lab animals, fish, all of that. They have publications that go through the literature and determine and calculate the best equations and determine which are the best equations from the literature. They apply them and compare them and do a tremendous amount of research to ensure that we are using the most accurate tools to predict our animals' requirements. So in this session, we're going to practice predicting energy requirements, especially maintenance energy needs of our animals. So when we talk about energy requirements for animals, it's important to remember that energy is measured in calories, and it's what is needed for the animals to do work. So, for example, I oversee a university sheep unit. When those ewes are lactating, raising twins, their work is producing enough milk to raise those lambs to weaning, as well as maintaining of the health and well-being of their body. If we're looking at performance horses, maybe horses that are being shown or Olympic level competition horses, their work is to perform at the highest ability they can. And so work can be defined a variety of ways. The requirements are generally separated, depends on the species, for maintenance and production. because a lot of times animals utilize energy more or less efficiently depending on what stage of production we're looking at. Generally, maintenance is considered the priority calorie need, because if we do not meet maintenance, everything else doesn't matter, because those animals are not able to maintain the health and well-being of their own bodies and their life, essentially. So how can we expect them to grow, lactate, run fast, work livestock, whatever the case may be? And so maintenance energy is a priority and a foundation principle that students of animal nutrition need to understand. I get this a lot in my college classes. Why should we care? We have AI, we have spreadsheets, we have software. Well, it's simple. Math and equations are critical thinking tools. And in agriculture, whether you're animal science, plant science, ag business, ag education, or communication, there's going to be equations and mathematics that you need to be able to do. Plus, software and applications and AI is only as good as the data we put in. And if we don't understand the mathematical process and don't put in accurate data, we're going to get junk answers. And so if you know the math and can have a perspective of what good answers are and what inappropriate answers are, that's what we need to have for the future, to be able to say if these tools that we are developing, and some that we probably haven't even thought of yet, are accurate and giving us good information that's going to be able to help us feed our animals. So I'm going to use a notepad just like I would a whiteboard, and we're going to kind of walk through a variety of examples. So we are specifically talking only about maintenance energy, and that is the calories needed to support life. Not any of the extra stuff, not lactation, not gestation, growth, none of the extra, just supporting life. Basic systems like respiratory, cardiac, neurological, digestive, those types of processes. And so as we look at some of the equations that the research and the National Research Council has generated, we need to have, I want to make sure we've got these reminders in the back of our head. One, maintenance only, not production. Okay, that's for all the species we're going to be talking about in this video. It's maintenance only. Two, this is the metric system. Okay, all these equations require weight in kilograms. Okay, so we're going to walk through how to convert pounds to kilograms, because 1 kilogram is the same as 2.205 pounds. I tell my students that's a graduation number, that when they're getting ready to walk across the stage for graduation, I can ask that question and they should know it. If you get hung up and struggle in converting pounds and kilograms, there are lots of converters online to help you do that, or you can have an app for your phone, whatever the case may be. Third reminder, order of operations matters. I cannot emphasize that enough. If you remember in high school or grade school, you talked about PEDMAS. That is a P right there. Parentheses, exponents, division, multiplication, addition, subtraction. Okay, that's going to matter, and that plays a role. Fourth, different species equals different measures of energy. which is fine, but we just need to keep that in the back of our mind. For example, in our ruminant species, ruminant, you think a ruminant nutritionist could spell ruminant. We're going to be dealing with the net energy system. And net energy my spelling is definitely off today, is the amount of energy that is going to the tissue level after we've accounted for losses from fecal energy loss, that undigested food in the feces. There's calories that are lost from the body in the gas and the urine, and also heat production. And heat production is a big one in ruminants, which is why they focus on the net energy system. For the horses and the equines, they utilize digestible energy. Their major loss of energy comes in the form of anything in the feces, so they utilize digestible energy. The monogastrics, swine, poultry, dogs, cats, all of those use what's called metabolizable energy, ME. Okay, that's what they utilize, and that is the amount of calories getting through the body to the organs and the tissue after fecal energy loss has been accounted for, after gas and urine losses have been accounted for. These species don't have huge heat of production, so we don't necessarily have to account for that. So each species is going to have a slightly different measure. Just bear that in mind as you're solving for these. Now, I have a summary sheet, and I will post these in a Google file link in the description of this video. But all of the species tend to have equations, all have equations for predicting maintenance. We have our ruminant species first, beef cattle, dairy cattle, sheep, and goats, because they're probably the most simple. And that's why I kind of start there. So let me make a note that this is all the ruminants. Okay. Then we move into our swine. And swine has two different equations depending on if they're a growing pig or mature sows. So you have to pay attention to what kind of a pig you're dealing with to know which equation you need to use. Horses also have two equations based upon size. And horses also have two equations based upon size. And so we've got the lightweight horses per se, things like under 600 kilograms, which is I think about I think it's just right around 1,300 pounds. So our quarter horses, thoroughbreds, all the ponies are going to fall into this light horse category. Now, some of the warm bloods, like the Hanoverians and some of those, are going to be right in between, depending on what they weigh. But all of the draft horses, the heavy horses, are going to be in this equation for over 600 kilograms. Clydesdales, Belgians, Percherons, those are all going to be in this heavy horse category. Then we get into some of our companion animals. And the dogs and cats both have series of equations that depend on activity level, obesity. The most complex equation we will do by far is either going to be for puppies or kittens post-weaning. There's a lot that goes into that, but it's a good learning opportunity about how we could use these mathematically. All right, so we're going to pull from these equations for some examples and walk through how we do this. I'm going to just keep that set right here. All right. So when we when I teach students to calculate maintenance energy requirements, there's 3 steps. First, step 1 is convert pounds to kilograms. It's the first thing you got to do, because you got to know what weight you're dealing with on a kilogram basis, because if you notice, especially like the equine equations, it's based upon their weight in kilograms. So that's always the first step that I have students do. The second step is to identify the appropriate equation. Now, this is where I love my ruminant species, because they only have one equation per species. Beef cattle is beef cattle is beef cattle. They use one equation. But other species do use more than one. And so we have to put on our critical thinking cap to be able to identify that appropriate equation. Third, plug in the data. Plug in data and solve. That's what we're going to be doing. Okay? So let's take a look at our first example. And we're going to do a beef cow. And she is weighing 1,000 pounds. Okay? That's going to be our first one. So the first step, if we stick to those 3 steps, is step 1, pounds to kilograms. All right, some of you might twitch a little bit, but remember that good old dimensional analysis stuff you had to do in chemistry to convert between units and all of that? This is where it comes into play. I do a shortcut, but I'm going to show you how it mathematically works out, and then you guys can go to the shortcut if you feel better. Okay, so if we have 1,000 pounds, okay, and we know that 1 kilogram is the same as 2.205 pounds, we know that pounds are going to cancel. 1,000 times 1 is 1,000. So this is going to boil down to being 1,000 divided by 2.205. Now that's normally where I start, but everybody's a little bit different. So however it helps you to see where units cancel when you're first starting out, I think that is critical. Realized I didn't have my calculator out, and I can't use my phone because it's the camera. Okay. So we're just simply going to plug that in. 1,000 divided by 2.205. And what we should notice that it's going to be about half. So I'm expecting somewhere between 400 and 500 kilograms just looking at the numbers. Because if we have 1 over 2, that's about a half. So we're dividing by 2. And sure enough, we are at 453.51 kilograms. Now, if you are a student in one of my classes, we round to 2 decimal places just to be consistent. If you are just watching this to learn about how maintenance energy calorie needs are calculated, you can round however you choose to. But now we have our body weight in kilograms. We're going to come back to our equations, and we're going to locate the beef cattle equation right here, which is in net energy for maintenance in megacalories per day. So step 2 is the equation. Step 2 and 3 are going to kind of happen together, the plug and solve. So net energy for maintenance, in ruminants, we divide net energy into maintenance and production. And this is in megacalories per day, is equal to, and if we look at our equation, 0.077 times body weight. And look, we have exponents to the 0.75 power. This is what is commonly referred to as metabolic body weight. So if we were putting this into thinking like an equation, this is what we're trying to resolve, right? So we would have X is equal to 0.077 times the metabolic body weight to the 0.75 power. Then we could just run that through our calculator. Okay, so I'm using my stats calculator, and I can just plug it in directly times, actually, I don't even have to use the parentheses, the 453.51. And for those on a calculator, you're either going to see, let me make a note of this, you're going to see a button with X to the Y or an caret button. One or the other is what you're going to see to go to an exponent. And so on mine, it is this button right here to the 0.75. So now I have typed in my equation that matches this right here. Enter. X equals 7.57, because I'm going to round to 2 decimals. That's just how my brain does it. And if we remember our units, and when you're first starting out, I always encourage you to label your units. Megacalories of net energy for maintenance per day. That's it. So this beef cow that weighs 1,000 pounds needs 7.5 to 8 megacalories of net energy for maintenance per day. And that's what the ruminant ones look like. We're going to do a sheep equation, because sheep and goats are in, they're in kcals versus mcals. So a little bit different type of number that you will get. So I'm just going to draw a line for a second example here. All right, so say we have a sheep. Okay, our sheep is a 250-pound ram, big sheep. Okay, so the first step is pounds to kilograms. So we can take that 250 pounds times 1 kilogram over 2.205 pounds. We know that pounds are going to cancel, and that's going to leave us with 250 divided by 2.205. Bring over my handy dandy calculator friend. 250, 2.205 gives us 113.38 kilograms. Okay, and so that's if you're using the dimensional analysis. You can go to where if you just take the weight divided by 2.205, you are going to get kilograms. But the second step in this problem is to pick the right equation and then solve it. So we're going to take a look at our ruminant equations, and here is our sheep equation. Now you'll notice that instead of it being in megacalories like the cattle, beef and dairy cattle equations are, this one is in kcals per day, and it's 58 kcals per unit of body weight, metabolic body weight. So the equation that we're going to go is still net energy for maintenance, but this time in kcals per day is equal to 58 times body weight to the 0.75. So we can now plug in our data, and in this will be X is our unknown, that's what we're solving for, equals 58 times 113.38 kilograms to the 0.75. Okay, so if you do not have a scientific calculator, or you're using your phone or something else that you can't see the whole equation at one time, this is where you'd remember your order of operations. Exponent, like if we had parentheses, that would be first, exponents, then multiply. Okay, so this would be the first step here, then multiply by 58. So 58 times 113.38 to 0.75. So x equals 2015.26. But now you're waiting, Selena, why is that number so much bigger than the other one? Okay. Beef cows, we're dealing with megacalories. Each megacalorie is 1,000 kcals. And so big animals like beef cattle and dairy cattle eat a lot that kcalories would not be practical to work in. Sheep, goats, swine, and smaller animals, they don't eat as much. So kcals is an appropriate metric or energy measure for those animals. So this ram needs just over 2,000 kcalories of net energy for maintenance each day to sustain his life, his maintenance, not asking him to go out during breeding season or anything like that. This is just his maintenance energy cost and energy or calories. Not too bad, I hope. Let's take a look at a couple others. We're going to do a pig example next. Just to kind of show you each of the species and kind of what that entails so you can make sure you're comfortable plugging these into the equations. So let's just say we have a growing barrel. That's a castrated male that is weighing 175 pounds. Okay, so first thing we do is pounds to kilograms. That's the first thing. So on this one, I'm going to immediately divide by 2.205. That's cutting out one step of writing out the full conversion. But if that's something that you need to do to help you stay on track, please do so. So if we take 175 divided by 2.205 in the calculator, we get 79.37 kilograms is what that 175-pound pig is weighing. Yay! Excellent, we've got it. Okay, so the next step is to find the equation and to solve. So let's look at our swine equations. We have two of them here. So this is a growing barrow. So that's our hint that this growing equation is the one we're going to use. Say if we had a gestating sow or a lactating sow, we'd use the other equation. Okay, so we're going to be using metabolizable energy now, not net energy, and it's 108 kcals per unit of metabolic body weight. So and again, that's in kcals per day, is equal to 108 times body weight. And remember, body weight must be in kilograms to the 0.75. So that's the same as x equals 108. Oops, I don't know why I did it that way. Okay, so let's put that in. So for this 175-pound growing barrow, maybe if some of you showed pigs or something, that rings a bell for you. We're going to do 108 times the metabolic body weight, which is 79.37 to the 0.75 power. That means that that pig needs 2,871.88 kcals of ME per day. So when this is part where we're getting like making sure we're thinking about correct answers, when we went from the cattle that were eating large amounts, it was like 7-8 megacalories. In horses, we may get up into the 20s on megacalories. But in the smaller species that are expressing energy requirements in kcals or kilocalories, 2,000 to 3,000 is going to be a much more appropriate number. Dogs and cats, it's going to be less than that by quite a bit because of size. They're only eating so much. So keeping in mind, what are realistic numbers? We're going to walk through a couple of the horse equations as well. I'm just doing examples. Feel free to skip ahead if you would like, if you're feeling comfortable with these. But I am going to do examples of every species so that people feel comfortable with them. I lied. We're not doing horses next. We're going to do dogs and cats first. Okay. Sorry, I have my notes on the side. All right, let's do a dog equation. Okay, say you have a 1-year-old. Let's go with a German short hair pointer. Those are very active dogs. And this one's being trained for hunting as a bird dog. So if you've ever been around any German short hair pointers, they're pretty active. And this is a young dog, not fully mature, still growing. Okay. And so when we get into the dog and cat equations, we have more options to choose from. And there's even more than this. This is just kind of a subset that I think we most commonly deal with. If you've ever watched the Iditarod race where they, in Alaska with the sled dogs, they have their own unique maintenance energy because of the stress and the amount of calories that they need to do what they do. And they're bred to do that and they love doing it. But it takes a lot of calories. So it just depends on what the animal is doing. If you have a house hippo, like I do, that would be an inactive pet dog. But for this scenario, a 1-year-old German short hair pointer is a young active adult. So this is the equation we're going to use. So this first thing we need to do is figure out what he weighs. An average German short hair is about 60 pounds. So step one is to convert from pounds to kilograms. So 60, I'm doing it off visual right now. That is 27.21 kilograms for that dog. Seems reasonable. Like I said, my first instinct when I look at converting numbers, I should have half of 60. So it's almost 30 kilograms. That's pretty close. That's how I ballpark and kind of make sure I'm in the range of realistic. Next, we're going to take the equation and solve it. So their energy measure is metabolizable energy, just like the pigs. And their measure is in kcals per day. Okay, so we're not in megacalories or anything like that. And the inactive young adult or the active young adult equation is 140 kilocalories per unit of metabolic body weight. And so that's what we're going to be plugging into. So our unknown value, X, the amount of calories per day they need, is equal to 140 times the body weight in kilograms to the 0.75 power. That's metabolic body weight. So if we run that through our trusty calculator, 140 times 27.21 to the 0.75 power equals 1,667.92 kcals of Me per day. That's what that dog would need to support just life, not to go above and beyond that. But that's the amount of calories that German Shorthair would need for maintenance. So these aren't too bad. We're going to do a kitten example. And this is where the equation is a wild one to do by hand, but it's important to understand how these work. So for the cats, we're going to do, we've got some, what kind of kittens? Siamese kittens. Somewhere the other day when I was thinking this lesson up, I saw a reference to the Siamese cats and Lady and the Tramp. So Siamese kittens. Their mature weight, now for the kitten equations, you need a mature weight. You may need to sometimes look up the average mature weight for a breed or type of an animal. And so they average about 11 pounds. These kittens are actually, we're going to say about 1.75 pounds right now. So thinking at weaning, just after weaning. And so we're going to have to do a little bit more digging, because with this equation, let's take a look at it first. You can see it is a lot more complex. It's using the base of a natural log and a few other things. And so when looking at this equation, this is where I'm realizing we need an actual body weight and the mature expected body weight. So we're going to take our information and do like we've done before and convert to kilograms. So we're going to take both the mature weight and the actual weight, which is the 1.75, and convert these both to kilograms. So 11 divided by 2.205, almost 5 pounds, or 5 kilograms. Sorry, I misspoke. 4.99 kilograms. That's what a mature Siamese cat averages. Let's do the actual weight, 1.75 pounds divided by 2.205. Just under a kilogram, 0.79 kilograms. That's what the kitten weighs. All right, now let's write out this silly long equation. And this is where order of operations is very, very important. So here it is, this equation right here. Okay, so I'm going to copy that across. So we're dealing with megacalories or metabolizable energy in kcals per day for these kittens. And that is equal to 100 times the body weight in kilograms, always kilograms. And you'll notice that we have different exponents for cats. They do not like to use the standard metabolic body weight like a lot of other species do. So that is 0.67 to the 0.67 power. And then we're going to multiply that times 6.7. Here's where it gets a little crazy. We got some brackets. So in this bracketed area, we have this E term. And E refers to the natural log, the base of the natural log. Okay, so I'm going to write it in like it's requested here, but then we'll explain what that is. And again, we have another exponent right there to the negative 0.189 times another variable called P. And so P is the actual weight divided by the mature weight. That's going to be a variable that we're going to have to calculate. Then all of this is minus 0.66. Looks scary as all get out, but let's break it down. Let's break it down. And so orders of operations. Let's first get all of our numbers into this equation. So we have X is equal to 100 times the body weight. So that's the actual body weight. 0.79 kilograms to the 0.67 power times 6.7. 6.7, just kidding. Had to throw it in there. It always pops up, and it popped up all semester with this equation. Times the base of the natural log, which is about 2.718. So that's a number that can be utilized. This is to negative 0.189 times P. And so I'm going to put P right there, but P is going to equal the actual body weight divided by the mature body weight. Okay, so that's what's going to go in right there, just because I'm running out of a room. Minus 0.66. Okay, so let's start breaking these variables down one by one. Let's solve for P first. So P equals 0.79 divided by 4.99. So if we solve for that, we get 0.16. If I rounded 2 decimals, let me show you on the calculator. Okay. So now we can plug that in to, now just kind of to get that one out of the way, let's go for that whole bracket, because I'm going to put that into my calculator. 2.718 times negative to the negative 189 times 0.16 power. Okay, see how that's going? Minus 0.66. Okay. And there are equation solvers online that I'm sure you guys know much more about than I do. But if we take that 2.7, oh, why did I say 9? That is 8. My bad, I saw 9. And that is going to be to the negative 0.189 times 0.16 power minus 0.66. So that is typing it in directly as it is. So this entire bracketed area gets reduced down to 0.31. Okay, so now if we bring in this front half, X equals 100 times 0.79 to the 0.67. That makes me giggle every time I say it, times 6.7 times 0.31. Okay, now you may wonder where all these constants and these values come from. That is years and years of research in the field that the National Research Council subcommittee on cat nutrition reduced down, and this is what they say is the most accurate way we can predict. We're still using a predictive tool to predict energy requirements. So we've got 100 times 0.79 to the 0.67 times 6.7 times 0.31. That is, X is about 177.36 kcals of ME per day for those kittens. Craziness, huh? All right, last one we're going to do is a couple of horse examples, because they're the only species that do not use exponents in some way to measure energy requirements. Okay, so let's start on the horse side of it with a 1,000-pound quarter horse. Okay. So like we've done before, the first step is to take that 1,000-pound quarter horse and divide by 2.205 to get kilograms. So it should be around 500. We actually did this math before on the beef cattle example. Okay. So we now know the horse's weight in kilograms. So this horse is under 600 kilograms body weight. So we are going to be looking at this first equation right here. 1.4 plus 0.03 times body weight in kilograms. So the digestible energy in mcals per day is equal to 1.4 plus 0.03 times the body weight in kilograms. So X equals 1.403 times the body weight, 453.51. Let's run it through and see what we get. 1.4 plus 0.03 times 453.51. Little over 15 megacalories of digestible energy per day. That's a reasonable number. Horses are going to be anywhere, like if you're near 20 double digits, you're in pretty good shape there. So that's how we would calculate the maintenance energy requirement for a 1,000-pound quarter horse. Now, if this horse was competing in, say, reining, working cow horse, barrel racing, whatever the case may be, then we would have to add the exercise energy demand on top of that. But right now, that's just for maintenance. Our second example is, I've got these written down, as 1,600-pound Clydesdale. Think like the Budweiser Clydesdales, big horses, big horses. So if we take that 1,600 pounds and convert it to kilograms, we wind up with 725 kilograms, 0.62. And so that horse is definitely over 600 kilograms in body weight. So we have this quadratic equation that we use. We have a couple constants that we got to make sure we transfer over exactly. And then we use body weight and body weight squared. So I'm going to transfer that over. So the digestible energy requirement in megacalories per day is equal to 1.82 plus 0.0383 times body weight in kilograms minus 0. And this is where I have to count zeros. So there's 4 zeros in there after the leading zero. And that's going to be body weight in kilograms squared. So I just want to make sure this is the equation we're working on. All right. So when we plug in that X is what we're solving for, 1.82 plus 0.383 times this number, the 725.62 kilograms, minus 0.123415 times 725.62 squared. That's what we're solving for. So in this example, X is going to give us, and this is where order of operations, I'm going to let the calculator resolve that, but make sure you transfer that this is a plus sign and a minus sign. Those are very important. In the equine equations, they're more quadratic-based equations. They're not more predictive regression equations like in the other ones. Else if I could type numbers in correctly. Trying to find my squared button. All right, we've got her plugged in. So this Clydesdale needs 21.71 mcals of DE per day. That's quite a bit more than the quarter horse, which makes sense. Much larger animal consumes a lot more feed. And so those are some examples of how we might use maintenance energy equations to predict the energy requirements of some of our animals. And they can work for a variety of species. And I hope this kind of helps you out a little bit. We're going to bounce back to the PowerPoint. So after going through this video, here's what I'd like you to ruminate on or think about or reflect upon is how do we use maintenance energy equations? Understand that equations can be useful in the workplace and that there needs to be some critical thinking to understand how to use those equations. And that math isn't super scary if you follow some of the basics that you already know. Orders of operation, pay attention to units, and make sure to check and verify your answers and understand what answers would be reasonable. Thank you, and I hope you enjoyed this episode of Applied Animal Feeding.